Assalamu alaikum. Welcome to lecture number 7. So today we are going to move to chapter 3 of the textbook, and the title of that chapter is Fourier Series Representation of Periodic Signals. Now, in our previous discussion, we used a representation of a system in terms of convolution sum and convolution integral. And the idea or the basic philosophy was that we somehow represented the signal as a linear combination of some basic signal. So let me write the statement. Signal representation as a linear combination of some basic signal. And in previous chapter, the basic signal that we used was unit impulse signal. And we found that any continuous time signal or any discrete time signal can be represented as a linear combination of unit impulse signals. And then once we represented the signal in terms of unit impulse, then for Lti systems, what we found was that if this input is represented in terms of unit impulse signal, then the output takes a very convenient form, and that is output becomes x of t convolved with h of t. And this representation is what we call as convolution representation. So in this particular chapter, we are going to see that it is also possible to represent signal in terms of some other basic signals that we have covered in chapter number 1. And once we use that particular basic signal, we get another useful representation for system, and that representation is then known as Fourier series representation. Now, before writing down the mathematical representation of Fourier series, let me also emphasize the importance of basic signals. So whenever you select any basic signal, so you try to use that signal which has some useful properties. So the two properties that we always look for in basic signals is so useful properties of basic signals. One useful property that we always look for in basic signal is that they should be able to represent a broad category of signals. So they can be used to construct a broad and useful class of signals. And second property is the response of an LTI system to each signal should be simple enough to provide us a convenient representation of system. Convenient representation for response of a system. And this is what we observed for this type of basic signal, which we have already used in previous chapter. So now if I want to select some other basic signal, it should have these two properties. So we will talk about these two properties in this lecture. But let's first of all look at the second property, which is the response of an LTI system to each signal. So that this each signal mean I'm talking about this basic signal. So if I want to select any basic signal, I want that if I apply that signal to an LTI system, the response of an LTI system should be simple enough. And this is what we are going to use for Fourier series. So in Fourier series analysis, our basic signal is complex exponential. And if you remember, we covered this signal in detail in chapter 1. So we will see that we can also use complex exponential signal, and we can construct a number of useful signals as a linear combination of complex exponential signals. So let's find out why this complex exponential signal is a very useful basic signal from LTI system point of view. So let's consider that there is an LTI system. So generally, complex exponential signals, we will consider both continuous time and discrete time complex exponential signal. So in continuous time, complex exponential signal is generally represented by e raised to power st. Okay, and in case of discrete time, complex exponential signal is represented by z raised to power n. And generally, s and z are complex numbers. So generally, s and z are complex numbers. So let's find out whether this signal has this property. Which property? Second one, the response of LTI system to each signal should be simple enough. And we can easily see this, and I will prove this in a short while, that if this is a continuous time system, and if you apply a signal of the form e raised to power st, the output of the system to this input is very simple enough. It will be same e raised to power st multiplied with some constant that I represent as h function of s. So what is the point that you can pick from this discussion is that complex exponential signal of this general form, it has a very convenient response for LTI system. E raised to power st is the input. You get the same signal e raised to power st in the output multiplied with this constant factor. Similarly, if this is a discrete time system, so if this is a discrete time system and if the input is complex exponential represented by this form, what will be the output? Output will be the same exponential signal z raised to power n and multiplied with some function which is h, and I will talk about it, what is h of s and which is h of z, but this is some factor. Now, this particular behavior of complex exponential signal in relation to LTI system, we can give a definition for this behavior. So let me write this statement. Signal for which the system output is a constant times the input is known as Eigen Function. Is known as Eigen Function of the system. And the constant factor is known as system's eigen value. So, two terminologies: eigenfunction and eigenvalue. So, what is eigenfunction? Eigenfunction is that function, and again, if you remember, from our perspective, function and signal is the same thing. Okay, so eigenfunction is that signal which, when you apply it to the system, the output of the system is the same signal multiplied with some constant. So with this definition, now you can clearly see this function is eigenfunction of LTI system. Why it is eigenfunction? Because when I apply this function as input to my system, I get the same input. I get the same input as output multiplied with some constant factor. And what is the name of this factor that will be multiplied with this eigenfunction? That particular constant is known as eigenvalue. So it means this thing is eigenvalue. And from discrete system point of view, this is eigenfunction. Why it is eigenfunction? Because when I apply this signal as input to LTI system, I get the same signal as output multiplied with some constant factor. And this constant factor will be then called as eigenvalue. Now, how we have arrived at this particular answer that if this is input, this is going to be the output. So we can make use of our knowledge that we developed in chapter 2 for LTI system. So what we know about LTI system? We know that for LTI system, the system output is the convolution of input multiplied with system impulse response. Okay. So let me prove this thing. So if x of t is the input, how I will find out output? Output of LTI system, if h of t is the system impulse response, we know that it's equal to x of t convolved with h of t. And we also know that convolution operator is commutative. So output is also equal to unit impulse response of LTI system multiplied with the n. And what is this convolution operator? So if you expand this convolution operator, so actually you have to solve this integral from minus infinity to plus infinity, h of tau x of t minus tau d of. So this is something which we already know from chapter 2, which we have covered in our previous lectures. Now, what we are saying is, we are now taking this x of t equal to e raised to power st. So let's find out if x of t is equal to e raised to power st. So what is going to be output or response of the system? So let me substitute this. So minus infinity to plus infinity, h of tau, and x of t minus tau, this is x of t. So x of t minus tau mean I need to replace t by t minus tau d of tau. Now our variable of integration is tau. So this e raised to power st, this can be taken out of this integral sign. So y of t is equal to e raised to power st. This term has been taken out of the integral, and what is left? H of tau e raised to power minus s of tau d of. Now this thing is a function. When you solve this integral, ultimately this is going to be some constant, and that constant will depend on the value of s. So what you get? What is the output? Output is e raised to power st, and this whole term can be represented by this notation. So I have proved right in front of you that if input is e raised to power st, output is also e raised to power st multiplied with this factor. And this is what I used over here. So now you know this is not just guess. I have proved this, that for LTI system, if input is e raised to power st, output will be like this. And this is the proof. And now you also know that what is this constant? This is known as eigenvalue. But if you want to calculate eigenvalue, now you know eigenvalue is equal to this thing. So h of s will be equal to integration of, and now you know this h of s is actually related to the system unit impulse response. What is this thing? This is unit impulse response. So h of s is the integral of unit impulse response of the system multiplied with this e raised to power minus s tau factor, and then integration with respect to tau. Now you can do the same thing for discrete time systems. Okay, so in this case, without going into the proof, I just mentioned that if input is z raised to power n, output is also z raised to power n multiplied by this. So how we get to this answer? So we have already covered discrete time LTI systems. So if you are dealing with the discrete time LTI system, and if input is x of n, output is y of n, and if the system impulse response is h of n, then we know that output is, let's say, h of n convolved with x of n. And if you expand this convolution operator, this is basically summation from k equal to minus infinity to plus infinity h of k x of n. But if you assume that input is complex exponential represented by this notation z is to power n, so let's find out if input is x of n equal to this, then what is y of n? So I can make use of this convolution expression. So x of n and now x of n minus k, it means I need to replace n by n minus k. Again, the summation is with respect to k. So this z is to power n is constant. I can take it outside of the summation operator. And we are left with this thing, h of k, z is to power minus k, where k is from minus infinity to plus infinity. And now you can clearly see that this thing is going to be some constant. And we can call this constant, or if we can represent this whole summation by a function h, which is dependent on z. So what is the output for output is z is to power n into h of z. So now if input is z of n, output is also same z is to power n multiplied by this factor, which is the eigenvalue. And now you can see this is what, now you know the answer. How I was sure that if input is z is to power n, output is also zn multiplied by this constant or amplitude factor. And now you also know that what is this h of z? This h of z is actually this summation. So now we also know that this eigenvalue for discrete time Lti system is summation of h, and you also know h, this small h is the symbol for unit impulse response. So this eigenvalue is actually related to the unit impulse response of the system. So now you know that complex exponential signals are very useful signals for Lti system. Why they're useful? Because the output of or response of Lti system is very simple enough. Complex exponential signal as input, you get complex exponential signal as output multiplied with some factor. And now we also know what is the expression to find the value of that factor. Now, what is the usefulness of this particular complex exponential signals? So we will come back to discrete time system later on in this particular lecture, and as well as in the next maybe 2 lectures. Our focus will be only on continuous time Lti system. Okay, so let's find out what is the usefulness of this signal for Lti system. What we are actually going to do is we are going to use this signal as our basic signal. And then we will see how can we represent any given signal as a linear combination of a signal like this. Okay. So it may be possible that the input of a system. So let's we can assume that so it may be possible that the input x of t is a linear combination of three complex exponential signals. So let's assume that x of t is like this: a1 e to power s1t plus a2 e to power s2t plus a3 e to power s3t. So our input is a linear combination of three complex exponential signals. Now, if we look at each of the component individually, so if this is the input, if only this component is applied as input to LTI system, so we know what will be the output. Output of the system will be the same signal multiplied with the eigenvalue. So what we will say, for this particular component, output of the system will be h of s1 into a1 e to power s1. Because this is the eigen function of the LTI system, so we know if eigen function is given as input to the LTI system, output is the same eigen function multiplied with the eigenvalue. Okay? Similarly, what is if we assume that only this signal component is applied to LTI system? So for this input, what will be the output? It will be h of s2 and then a2 e to power s2t. And similarly, for this particular input, output will be h of s3 a3 e to power s3. Now, the actual input is not only this one or this one, it is addition of these three. And we know for LTI system, because the linear system, so it will obey the principle of superposition. So if input is the addition of these three, so output will also be the addition of the corresponding responses. So I will say output y of t will be equal to this term plus this term plus this term. So you can see the advantage of representing the signal as a linear combination of complex exponential. If we can represent our signal as a linear combination of complex exponential, then our output is also conveniently represented as a linear combination of corresponding responses. So if I can generalize this discussion, so in case if our input is a linear combination of number of terms, so I will now use this compact representation that there are number of terms with respect to variable k, and we have ak e to power skt. If such type of signal is given as input to LTI system, what is going to be the output? We now know that because complex exponential signals are eigenfunction, so the output is also going to be the linear combination with respect to k. So we will get the same ak e to power skt, which is the eigenfunction, and it will be multiplied with the corresponding eigenvalues for different values of s. So this is the advantage of representing the signal as a linear combination of complex exponential. And when we use such signal as input to LTI system, we can easily represent or calculate the output of our LTI system. Now, coming back to the Fourier series. In case of Fourier series, this complex exponential signal, which I represented in this representation, e to power st, and I mentioned that S is complex. But for Fourier analysis, we will only consider a special value of S, and that is when S is purely imaginary. When S is purely imaginary. So let's talk about this aspect. So for Fourier analysis, S, which is generally complex, we will assume that it is purely imaginary. So as a result, the basic signal becomes e raised to power j omega. We are going to use this signal as our basic signal. Now, whatever were the properties of e raised to power st, the same properties are obeyed by this signal. In other words, if e raised to power st is the eigen function of Lti system, so e raised to power j omega t is also eigen function of Lti system. The only thing that is going to change is, so now what we will say is that if Lti system, if input is e j omega t, what is going to be the output? Output is also going to be the same signal, e j omega t, multiplied with eigen value, but now eigen value will be not function of s, it will be function of j omega. So this is our eigen value, and this is our eigen function. And we already derived the expression of h of s, and now only thing that we need to do is replace s by j omega. So now if I want to calculate h of j omega, it will be equal to integration from minus infinity to plus infinity h of tau e raised to power minus j omega tau dx. What was the expression of h of s? So let me write it over here. So when we calculated h of s, it was equal to integration of h of tau e raised to power minus s tau dx. So you can clearly see all I have done is replace s by j omega. Similarly, this is for continuous case. Fourier analysis is applied in continuous case as well as discrete case. So in case of in a discrete time case, our signal was z is to power n. And if you remember, I mentioned that this z is a complex number. But for Fourier analysis for discrete time system, we will assume that this z is such a complex number whose magnitude is equal to 1. So it means what type of value z should have? If z is equal to e raised to power j omega. So now this is a complex number, but you can see that its magnitude is always equal to 1. Its magnitude is always equal to 1. So now what will be the form of signal z raised to power n? It will become e raised to power j omega n. So for continuous time case, we will use this signal in Fourier analysis, and for discrete time systems, we will consider this signal as our basic signal. So whatever properties were mentioned for this signal, so we use this, we prove this thing that z raised to power n, which is a complex exponential signal, this is the eigen function of Lti system. Now e raised to power j omega n is also complex exponential signal. So this is also going to be the eigen function of Lti system. So if you apply this signal as input, so what is going to be the output? Output is going to be the same signal multiplied with eigen value. So previously I was representing eigen value as h of z. So previously we were using h of z, but now we know that z is now a special z, which is equal to h omega. So this eigen value is going to be represented by this e of j omega. And if you remember, h of z was equal to h of k, z is to power minus k, where k is from minus infinity to plus infinity. So what is the expression for this particular eigen function? It will be equal to summation h of k, and in place of z, I will write e raised to power minus j omega k, where k is from minus infinity to plus. Now let's take a simple example to see the application of this complex exponential thing. So let's assume that there is a system whose input output behavior is like this. Y of t is x of t. So if input to this system is complex exponential, and that is, let's say, e raised to power j 2t. So what is going to be the output? So input-output relationship is simple enough. Output is simply the shifted version of input, and how much shift is, that is equal to 3. So if input is like this, output will be equal to e raised to power j2, and in place of t I will write t minus 3, and then you can express this as e raised to power minus j6 and e raised to power plus j2t. So now you can see that we have a very convenient representation for the system output. The input was complex exponential. Complex exponential. And just we proved that complex exponential is the eigen function. So if it is an eigen function, the output will also be the same complex exponential. And you can clearly see in the output, we have the same complex exponential multiplied by some constant factor. So actually this is h of, because this is j2, so this is actually h of g, which is equal to e power minus j6. So this is the eigenvalue. So through this simple example, you can see that for Lti system, if input is complex exponential, output will also be the same complex exponential multiplied by this eigenvalue. Now with this understanding, let me come to the Fourier series representation. So one thing that you need to keep in your mind, that there are two tools that we will use in Fourier analysis. One is Fourier series, that is the topic of this chapter. And the other tool that we use is known as Fourier transform. So what is the difference between these two? So Fourier series, which is the topic of this chapter, Fourier series is used for periodic signals. Whenever you represent any signal in its Fourier series representation, it means the signal is periodic signal. So it is for periodic signal. And when you use Fourier transform, usually you use Fourier transform for non-periodic signals. But we will look into the detailed explanation of this. Fourier transform is a general transform. So even you can use Fourier transform for periodic signals under special circumstances. So Fourier series is used for periodic signals generally. We cannot use it for non-periodic signals. Fourier transform is usually used for non-periodic signals, but we can also use it for periodic signals. So in this chapter, our focus is on Fourier series. And as I mentioned, we will first consider periodic signals in continuous time. So first of all, we will talk about Fourier series representation of continuous time signals. So we want to look at Fourier series representation of continuous time periodic signals. So we will develop an equation, and that equation will be known as Fourier series, and representation that we will develop, it will be only valid for continuous time signals, which must be periodic. So let's come to the basic definition of periodic signals. So we have already talked about this property of a signal, that if any signal is periodic, it must fulfill this condition. So for periodic signals in continuous time, x of t must be equal to x of small t plus capital T for all time. Where so when we say signal is periodic, we usually talk about the fundamental period of the signal, which is the smallest value of this. So T is the smallest positive non-zero value and is called fundamental period. And we also use omega naught, which is equal to 2 pi by capital T. And this omega naught is called fundamental frequency. So this is the general definition for periodic signal. But two common periodic signals that we have already covered in this course is sinusoidal signal and complex periodic exponential signal. So as an example, which two signals that we have covered and they are periodic, one of the signal is x of t is equal to cos omega naught. So this is a sinusoidal periodic signal. And other signal that we covered is e to power j omega naught t. This is a periodic exponential signal. And we also use the concept of harmonically related signals. And if you remember, when I was covering that topic, I mentioned that this concept will be used later on in this course. So now this is the time that we use that particular concept of harmonically related complex exponentials. So just to remind you, what was the concept? That there are number of complex exponential signals. All of them are periodic with a different fundamental period. But why they are called harmonically related? Because there is one period that is going to be common for all of the complex exponential signals. So based on that, we call them harmonically related complex exponentials. And what was the mathematical representation for such a set of signal? So I use this notation, phi sub k equal to e to the power j k omega naught t. Or if you want to represent this expression in terms of fundamental period, so you can replace omega naught by 2 pi by capital T. And this k is an integer, so we have minus plus 0, minus plus 1, minus plus 2, minus plus 3, and so on. So what is the relationship? So if you put different values in this expression, so for every different value of k, you will get a different signal. So phi 0, phi 1, phi 2, phi 3, all of them are complex exponential signals. All of them are periodic. And what is the relationship? All of these signals, their fundamental frequency will be multiple of omega naught. So let me write this statement. Each of these signals has a fundamental frequency that is multiple of omega naught. And each is periodic with period t. So this capital T, this is the common period for all of the signals. So for k equal to 1, if you put k equal to 1, you get a signal e to the power j omega naught t or e to the power j 2 pi capital T into small t. This is a signal which is having a fundamental frequency of omega naught and fundamental period of capital T. Okay. If you put k equal to 2, you get 2 omega naught t, which means now this signal has a fundamental frequency which is twice of this one. And because its frequency has doubled, so its fundamental period will be half. So for k equal to 1, you will get a signal for which the fundamental period will be half of t, which means it will have a period of capital T by 2. But a signal whose fundamental period is capital T by 2, capital T is also going to be the period of that signal, even though it is not the fundamental period. So for signal k equal to 1, the period was T. For k equal to 2, T is the period. For k equal to 3, T is going to the period. But what is the difference? This T is the fundamental period for this signal. But for this signal, capital T is not the fundamental period. But it is still the period. For k equal to 3, capital T is the period, even though it is not the fundamental period. For this signal, fundamental period is T by 2. For this signal, fundamental period is T by 3. But any signal whose fundamental period is T by 2, then capital T will also be its period. A signal for which period is capital T by 3, T is also going to be its period. And you can keep on changing the value. So what is the reason that we call these signal harmonically related? Because all of them have one common period, that is T. Now, once we have this idea, what we can do, if we take a linear combination. So a linear combination of harmonically related complex exponential a linear combination of harmonically related complex exponential is also going to be periodic with period capital. So it means linear combination means if I use this representation, summation, some factor, constant factor, and then e to the power j k omega naught t for k equal to minus infinity to plus infinity, that is going to construct a signal x of t, and this signal will be periodic with this period. So periodic with period t. So if we take a linear combination of this set of signal, the linear combination of all of these signals will generate a signal that I am calling S of t, and this is going to be periodic with period. Or in other words, you can interpret this equation in this manner, that if we have any periodic signal, which I'm calling the x of t and which is periodic with capital T, if I want to represent this signal in terms of complex exponential signal, I can use this equation. And this is the equation that is known as Fourier series. This is what we call as continuous time Fourier series. Continuous time Fourier series. Now, you also need to keep this thing in mind, that this k, which is shown to be varying from minus infinity to plus infinity. So if you consider different values, if you put k equal to 0, so for k equal to 0, we know that we will get a constant function. If you put k equal to 0 over here, you will get 1, which is a constant signal. Okay? And we already know that constant signal is having a fundamental period equal to 0 and whose fundamental period will be undefined. Okay? If you put k equal to 1, if you put k equal to 1, you get a signal having fundamental frequency omega naught. And this particular frequency component is known as first harmonic component. Okay? So if you put k equal to plus 1, or if you put k equal to minus 1, the components are called first harmonic components. And if you put k equal to +1 or +2 or -2, then they are known as second harmonic components. Second harmonic components, and so on. And if you put k equal to +n or -n, then we will call those components as nth harmonic component. Nth harmonic components. So any periodic signal, when you expand this summation operator, you will get number of terms. You will get a constant term for k equal to 0. Then you will get the fundamental component or first harmonic component. Then you will get second harmonic component, third harmonic component. So depending upon what is the value of k, this expression will give us number of components that we call as harmonic components. So for periodic signals, we always use this terminology of what are different components of present in the signal as harmonic components. Okay. Now, just to give you a visual representation, let me go back to this figure. Let's assume that you have a signal whose equation is given to you as it's like this: 1 + 1/2 cos 2 pi t plus cos 4 pi t plus 2/3 cos 6 pi. Now this signal, which is represented as a linear combination, so this x of t is periodic signal. And it is made up of number of components. So this is the constant component. This is the first harmonic component, which is having this fundamental frequency. This is the second harmonic component, and this is the third harmonic component. And the original signal is made up of summation of these four components. So first component, second component, third component, and fourth component. So just to give you a visual idea, if you assume that if you consider only the first component, which is constant one, so what will be the graphical representation? Graphical representation is this. For all time, with respect to time, if you plot this signal, so you will get this straight line. Okay. So this is, let me call this as x0. X0. If you consider only this first component, this is going to be the graph of your signal. Okay. Now, if you look at the second component, I am going to call this as x1t. If you plot this signal, your signal is going to be like this. This is the shape of a signal, which is 1/2 cos 2 pi. And now if you add first two components, so if you add this component and this component, which means if you add this thing and this thing, you will get this signal. You can see that this signal is the summation of x0 plus x1t. So when you add this constant level signal to this signal, you can see that the signal has shifted up and you get this signal. And now if you consider the third component, which I can call as x2t. So if you plot only this signal, this is going to be the shape of your signal. But now if you add the three components, which means this component, first component, second component, and third component, if you add these three together, this is going to be the shape of your signal. And you can clearly see that this is periodic signal. This is also periodic, but now because of the addition of third component, the shape of the signal has changed. And now in the final stage, if you consider only this signal, which I call as x3t. x3t is equal to 2 by 3 cos 6 pi. If you plot the signal, this is going to be the shape of your signal. Okay. And if you add all of them together to get to the actual signal x of t, you add them together, which means this signal, this signal, this signal, and this fourth signal, your resultant signal is going to be x of t. And you can clearly see that it's a periodic signal. It is repeating its pattern. And if you break down now, if you go in the reverse process, that if this is x of t, but if you break it down, actually it is made up of this signal, this signal, this signal, and this signal. So this example is giving you an idea that when you represent any signal in Fourier series, actually Fourier series helps you to break down your signal and helps you to look at your signal as if it is made up of some basic signal. Okay. In this example, you may say that I use this representation. Let me go back. So Fourier series, I use this. Yes. This was our Fourier series. And you can see in Fourier series, we have this exponential signal. But the example that I have shown you, it consists of x of t represented as summation of sinusoidal signal. Okay. But you already know that sinusoidal signals and periodic exponential signals are closely related. Remember, this is something which we covered already, that this signal and this signal, they are closely related. So most of the time, we will be using this form of Fourier series, which will involve complex exponential signal. But when our signal is a real periodic signal, then it's better to represent it in alternate form, and that involves trigonometric functions, that is sine and cosine. So let's find out what is the alternate representation of Fourier series. So maybe in your mathematics courses, you might have used a Fourier series, which may be different than this one. So this representation, this form of Fourier series is known as complex Fourier series. This is complex Fourier series. What is the alternate form? So let me derive the alternate form. So as I mentioned, we normally use the alternate form for real periodic signal. So let me say for real periodic signals. We use alternate form of Fourier series as derived below. So first of all, when we are talking about a real periodic signal, what does that mean? It means that if x of t is real signal, it means even if I take the complex conjugate of that signal, there will be no change in the signal. So x conjugate t is same as x of t. In other words, if you have a real number 2, if I ask you to take its conjugate, that must be equal to 2. So x of t, its complex Fourier series representation is this one. Ak e to the power j k omega naught t, where k is from minus infinity to plus. So let's take the conjugate on both sides. So on the left hand side, we will get x conjugate, and on the right hand side, ak conjugate, and e plus jk will become e power minus jk omega. So by taking the complex conjugate on both sides, we will end up with this. Now, because x of t is a real number, is a real signal, so x conjugate t can be replaced by x of t. So we get this thing. Now, on the right hand side, replace k by minus. And we can do this because the interval of summation is from minus infinity to plus infinity. So even if you change k by minus k, you can still cover the whole interval minus infinity to plus infinity, because minus infinity will become plus infinity and plus infinity will become minus infinity. So this substitution is not going to affect the answer. But let's see what will happen to the mathematical form. So a sub k will become a sub minus k conjugate, and e raised to power minus jk will become e plus jk. Now, another thing that you can notice over here is, yes, this one. This is x of t, okay? And we get expression of x of t like this, and we have ak over here. If you compare this equation, let me call it equation 1, and then if you compare this with equation number 2, you can see the only thing that is different is this thing. So if x of t is equal to this thing as well as x of t is equal to the previous thing, so it is only possible if this thing and this thing, they must be equal. They must be equal. So comparing 1 and 2, we get a result that a k must be equal to a minus k conjugate. And sometimes we write this in the different form, and that is if you take the complex conjugate on both sides. So now on the left hand side, we get ak conjugate, and the conjugate and conjugate will cancel out. So we will get ak conjugate equal to a minus. So this is true for real periodic signals only, okay? It's true only for real periodic signals. Okay, now let me continue this proof. So let me separate the value for k equal to 0. So on the right hand side, if you put k equal to 0, so you will get a0. So now we have to start from, let's say, 1 to plus infinity. So now inside the bracket, I am going to use two terms because this interval is from minus infinity to plus infinity. I have already separated the zero value and 1 to plus infinity. So it means the other term is minus 1 to minus. But what I can do? I can say ak e to the power j k omega naught t. And second term, I will say a minus k e power minus j k omega naught. So this term was replaced by ak because of this result. And then what I have done is I have separated this summation operator into this form. So now this is the zero term. This will include plus 1 to plus infinity, and this term will involve minus 1 to minus infinity. Now we have already proved this thing that a minus k is equal to ak conjugate. So this a minus k can be replaced by ak conjugate. And now you can clearly see that the two terms which are inside this square brackets, they are complex conjugate of each other. They are complex conjugate of each other. In other words, if you take the complex conjugate of this term, you will get this term. And you already know from your basic complex number that if you have a complex number z, and then you add it with the complex conjugate of that number, that addition is equal to 2 times real part of z. Okay. This is the result that you use in your complex number analysis. So this is what I'm going to do. This number plus the complex conjugate of this thing can be replaced by, I will say 2 times real part of ak e to the power jk omega naught, where k is from 1 to plus. Now all we need to do is find out what is the real component of this complex number. Now this ak is a complex number, okay? ak is complex. Now there are two possibilities. We can either represent this complex number in polar form. So we can say this ak is a number whose magnitude is, let's say, capital AK, and its phase is, let's say, theta. This is one possibility. So we can use this one, or an alternate possibility is that complex number can also be represented in terms of its real part. Let's call that real part as bk, plus its imaginary part. Let's call this as ck. So these are two possibilities that we can use over here. Okay, so let me use the first one, okay, and then see what we get. So x of t is equal to a naught plus 2 times k from 1 to plus infinity 2 times, sorry, not 2 times, real part of ak, and then e to the power j k omega naught t plus theta. So in this case, what I have done is I have used that small ak is equal to its magnitude form and its polar form. Okay. So in place of ak, I have substituted this, and then I have combined this exponential factor with this exponential. So now you know that what is the real part of this thing? Real part of e raised to power j omega naught must be equal to cosine of function, Euler's relationship. Okay, so what you get? You get a naught plus 2 summation k equal to 1 plus infinity, and then you have ak cosine k omega naught t plus t. So this is the alternate form that I was talking about, which is representing the periodic signal as a linear combination of cosine function, which is a sinusoidal. This is also Fourier series. Okay? So now we call this as trigonometric Fourier series. Fourier. And what is the other possibility? Other possibility is that you replace this ak by this representation, and then you find the real part. So what you will get? I'm not going to do that in so you can easily do that. X of t can also be represented as a naught plus 2 times k equal to 1 to plus infinity, and you get dk cos k omega naught t minus ck sine k omega. So sometime you will see Fourier series involving both sine and cosine functions. So actually that is derived through this particular form. So this is trigonometric Fourier series as well as this is trigonometric. So that is the reason that if I go back to the example that I was solving, this one, this signal was periodic, and you can see it was represented in trigonometric Fourier series. So you can see we have cos function. So this was basically Fourier series in its trigonometric form, and which involved only cosine. So basically, it was using this form. Now, as I mentioned, we will be making use of Fourier series, which is represented in complex form. Now the question is, if you want to represent any periodic signal x of t in this form, the unknown that you need to find out is ak. The question is, what is the value of ak? How you will find out the suitable value of ak? Now, we can assign a name to this particular number to this particular variable in our expression. So this ak is known as Fourier series coefficient. This is more of a mathematical name, but from signal and system perspective, it's better to call this particular variable as spectral coefficient of x of t. And once I derive the expression for ak, and then I will solve one example, and that example will help you to understand this meaning, that why we are calling ak as spectral coefficient of x. First, let's find out how to determine ak. Okay, so this is the equation. And we want to find out expression for it. So what you can do, you can multiply both sides by e power minus j omega n t. So I will multiply e power minus j n omega naught t on the left hand side as well as on the right hand side. And then I will integrate both sides over the period. So over period, let's say we start from 0. So it's from 0 to capital T. We can combine these two terms. So we get E plus J omega naught T, and we have K minus N. Let me change the order of operation on the right hand side. So let me bring the summation operator outside. And this constant also outside of the integration. So we are left with this integral. So now all we need to do is find out what is going to be the answer of this integration. So there are two possibilities. One is, what is the relationship of this k and n? If k is equal to n or if k is not equal to n, these are two possibilities. So let's find out this integral. So if k is equal to n, so that is straightforward. If k is equal to n, this will be equal to 0. So e raised to power plus j0 means 1. So if you integrate 1 from 0 to t, you will get t. The other possibility is if k is not equal to n, then this integral will become equal to 0. So it means when we take the summation operator for minus infinity to plus infinity, the only non-zero value that you will get is when k becomes equal to n. So when k becomes equal to n, this ak will become an, and it will be multiplied with this. For all of the values of k, the answer is 0. So based on that, we will say that on the left hand side we have x of t e to the power minus j n omega naught t d of t 0 to capital T, and on the right hand side we get t a n, and which means am is equal to 1 over t integration from 0 to t x of t e to the power minus j n omega naught t. Now, we have changed the variable from k to n. So even if I replace this n by k, what will happen to this? Because in original expression, we are representing the coefficients by ak. So in this expression, even if I now change n to k, so what will happen? Only thing is now our expression will be in terms of k. And this is what we were looking for. We were interested that in this representation, what is going to be ak? So now we know that ak can be calculated through this. So whenever we talk about Fourier series, so there are two equations that we will be using. One is this one, and second one is x of the summation ak e raised to power plus j k omega naught t of t. K is equal to minus infinity to plus infinity. So Fourier series will always correspond to these two equations. And sometimes we use some names for these two equations, okay? So the first equation, which is representing ak, which are Fourier series coefficient or spectral coefficient, it is known as synthesis equation. And this equation, which is representing x of t, sorry, just make a mistake. This one is synthesis equation. This one is analysis equation. So Fourier series means these two equations, analysis equation and synthesis equation. Now, you should also remember that this ak, for every different value of k, you will get some answer out of this analysis equation. So as a simple case, if you put k equal to 0, if you put k equal to 0, so the coefficient, so let me say for k equal to 0, what will happen? You will say a naught, and you get 0 to t, and then you have x of t dx, because this term will become equal to 1. Now, this is coefficient a naught, but from signal and system perspective, this is what we called as DC component of the signal. DC component or constant component. So whenever you use this equation to calculate different Fourier coefficients or spectral coefficients, so this special component which you get for k equal to 0 will give you the DC component that is present in this signal. And for any other value of k, you will get, as I mentioned, if you use this equation for k equal to 1, and then you solve this integral, you will get the first harmonic component. So actually, when you calculate ak, these numbers will tell you what are different components that make up this signal. So the value of Fourier series coefficient will tell you the portion of different frequency components that are present in this signal. So again, if I go back to the one example that I solved, this one. So if you look at this signal, this is our original periodic signal. So actually, this signal is made up of different frequency components. As you can clearly see, it consists of this constant component. So actually, this was the DC component. Now, how much is this magnitude? Of course, this signal magnitude is 1. So it means when you evaluate this expression, you will get A naught equal to 1. So this 1 is telling you how much DC component is present in your signal. And similarly, for all of the components. But important point is all of these, in this example, I have plotted different component as a function of t. So along x-axis, this is time. But when you plot this AQ, and later on I will solve one example as well. So when you find out values of k with the help of this analysis equation, so then you will plot those values along x-axis with respect to k. And if you remember, k is a discrete number. K cannot have all possible values. K can be either 0, or it can be plus minus 1. It can be plus minus 2, and so on. So it means when you annotate x-axis, you need to take discrete values. So it means you need to take 0, then you will say plus 1, then you will say plus 2, then you will say minus 1, and then you will say minus 2. So these are values of k. So if you get some value of A naught, if you get some value of A naught, then what you will do, you will draw a vertical line. Let's say you will draw a line like this, depending upon what is the value of A naught. Okay. Similarly, if you get some value of A1, so it may be plus, it may be negative as well. So then you will draw a line like this. And if for any, let's say you may get some value for A minus 1 as well. It's also possible that for some number, maybe for k equal to 2, the value comes out to be equal to 0. Then you will not draw any line over here. It means there will be nothing at this point. So this, when you plot this is what we call as line spectrum. And because of that reason, if you remember, I mentioned that AKs are known by the name of Fourier coefficients, but they are also known as spectral coefficients. And spectrum is related to frequency. So actually, this 0 means if you have something at k equal to 0, it means this is the DC component. It means 0 frequency component. If you have something at this number that is k equal to plus 1, so k equal to plus 1 means the frequency is omega naught. K equal to plus 2 means the signal frequency component is 2 omega naught. Minus 1 means signal frequency is minus omega naught. Minus 2 means signal frequency is 2 omega naught. Minus 2. Actually, this is the spectrum. And that is that utility of Fourier series. When you express signal in terms of its Fourier series, so actually you find out what are different frequency components present in your signal. So most of the time you will be looking at signal in time domain. So you plot your signal with respect to time. So that is the time domain representation of your signal. But Fourier series allows you to represent a signal in frequency domain. And sometimes frequency domain information is more important for us. So whenever you are interested in frequency domain analysis of a signal, you have to use Fourier series tools. So let me solve one or two examples related to Fourier series. So signal is given to you sine omega naught t, which is the simplest periodic signal that you can consider. So we want to find out its Fourier series representation. Find its Fourier series representation. Now, this is a very simple example, but as a general rule, whenever you are asked to find out a Fourier series representation, so you will start with this equation. You will say if this signal is having Fourier series, so it must look like this. And then the next thing that you will do is find AK with the help of this equation. Okay, one thing that I forgot to mention is in this two equations, you can see that I have shown that the interval of integration is from 0 to capital T. But it doesn't matter. Even if you integrate it over any interval, but if it involves one period, then it is going to give you the same answer. So what it means that I just need to say integration over one period. What is the difference? Previously, I was saying 0 to capital T, which means that I am explicitly saying that you should start from this time 0 up to capital T. But now when I replace this by this representation, it means now I am saying you can integrate over any interval, but that interval must be equal to one period. Okay, so this is over one period. Okay, and the reason, if I further go back, this one. In this case, I mentioned that for k equal to t, this integration will give you t. So even if you integrate not from 0 to t, if you integrate over any time interval, you will still get the same. It means, just to be more specific, you can start from t, and then you, in order to cover the whole time period, you must go up to 2t. If you start from minus t, you must stop at 0. If you start from minus 2t, you must stop at minus t. So you can see this whole interval is over. This is something that I forgot to mention. So it means if I want to solve this, so you need to take this expression, which we derived before. This is what you will do normally. But for this simple example, rather than finding out the Fourier coefficient through this, we can make use of Euler relationship. We already know that this x of t can be represented as e raised to power j omega naught t plus e raised to power minus j omega naught t, and then whole divided by 2. So I can take 1 by 2 factor over here and 1 by 2. This is using Euler's relationship. And now you can clearly see that we have represented our signal in terms of our complex Fourier series. And these are the coefficients. So 1 by 2. Sorry, I just made a mistake. Let me correct that one. X sine omega t is equal to minus, and this is minus, and this is j. So this 1 over 2j and minus 1 over 2j. What are these two numbers? They are Fourier coefficients. If you look at this representation, this ak is related to this k number. So over here, k is equal to 1. K is equal to 1, so it means this must be equal to a1. And this is minus, so minus means this must be equal to a minus 1. So what we can conclude from this representation? For this signal, a1 is equal to 1 over 2j. A minus 1 is equal to minus 1 over 2j. And for all other values, ak is 0. If k is not equal to minus plus. Now, if I draw the line spectrum for this case, if I plot Fourier coefficient with respect to k, so I just need plus 1 and minus 1. Okay? And then I can say at plus 1, I have a line. And then I have a line at minus 1, which is in the negative direction. So this is A1, and this one is A. This is the line spectrum. So that was what I was mentioning, that if you plot this thing, normally this is something that we are always comfortable, and we always visualize sinusoidal signal, and we say this signal is like this. But the same signal, when you use Fourier series, this same signal is now represented in this manner, and this representation is going to help us to look at this signal in this form, and this is now related to spectrum mean frequency. So this is telling us that there is theoretically or idea or mathematically there are two frequency components. So plus 1 means plus omega naught, minus 1 means minus 1. So we know that there is no such thing as negative frequency in practical sense. It is this negative frequency is only because of this complex signal. This complex representation allows us to have this plus and minus, but in reality, this signal is having frequency of omega naught. So, and this is exactly represented by this figure, that there is only one frequency component present in this. Okay. Now, let me take another example. You may be given a signal which is like this: 1 plus sine omega naught plus 2 cos omega naught plus cos 2 omega naught plus 5. Now, this signal, as it is clear that it is made of some constant signal and then sine, cosine, cosine, so it is a periodic signal, but we want to represent it in the complex Fourier series representation. So I want something like this. I want to represent this signal in this way. So again, rather than finding coefficients with the help of analysis equation, because we have sine, cosine, so we can make use of Euler's relationship. So you can always convert sine function in terms of exponential function, cos function, and similarly this as well. So if you do that, so I will say using Euler's relationship, you can transform this signal in this manner: 1 plus 2j e to the power j omega naught t plus 1 minus e to the power minus j omega naught t plus 1 by 2 e to the power j pi by 4 e to the power j 2 omega naught t plus 1 over 2 e to the power minus j pi by 4 e to the power minus j 2. Using Euler's relationship, you can represent this signal. And now you can easily find out what are the Fourier series coefficients. Fourier series coefficients. So this it is a naught. This one is A1. This one is A minus 1. This is A2. And this is A minus 2. So you can see that this is e to the power j0. So this is a constant frequency component, DC component. Over here you have e to the power j1. So this is A1. You have minus 1, A minus 1. You have 2 omega naught. So this is the second harmonic component. And then you have minus 2, which means A minus. So now you can see that Fourier coefficients, they are, in this example, they are complex. So sometimes you may deal with a periodic signal for which Fourier coefficients are real. Sometimes you may deal with signal for which Fourier coefficients are imaginary. And generally, Fourier series coefficients are complex. And you can clearly see A1 is a complex number. This is a complex number. This is also a complex number. So whenever you plot, I was mentioning that it is important that whenever you are asked to find a Fourier series, you should be able to plot as well. And what we are interested to plot, we are interested to plot Fourier coefficients AK. Now, if AK is a real number, then you need only one graph. You need only one graph. Okay. But if Fourier series coefficients are complex, which are in this case, then you need two plots, one for the magnitude and other for the phase. So if you plot the magnitude and phase for this example, you may get a graph like this. Yes. You can see this is the magnitude part and this is the phase. So this is A0, this is A1, this is A minus 1, this is A2, and this is A minus 2. And you can see all of the other components are 0. And this is the phase part. So constant signal, its phase is 0. And then this A1, its phase is negative. A minus 1, its phase is positive. A2, its phase is positive, and A minus 2, its phase is negative. So you can see this is the magnitude spectra, and this is phase spectra. Now, another example that is very important from this point of view, that when Fourier first introduced this concept of Fourier series, and he proposed that any periodic signal will always have a Fourier series. So most of the famous scientists of that era, they were opposed to this idea of Fourier. So they were reluctant to accept this idea that all periodic signals will have a Fourier series. And one of the example that Fourier proposed that this particular signal will have a Fourier series, but scientists, they objected to that idea, is the example that I'm going to talk about now. So this is a periodic signal. As you can clearly see, this is a signal which is repeating itself after this time interval, capital T. And actually, this is an example of what we call as periodic square wave, a very common periodic signal that you will find in different books. So if this signal is periodic, then according to Fourier, it must have a Fourier series. And Fourier used this example and he calculated the Fourier series. So let's find out what is the Fourier series representation of this periodic signal. We are assuming that this is minus T1 to plus T. Okay. Now, if I want to represent this signal in its Fourier series representation, so I need to find its Fourier coefficients. Okay, so it means that so x of t according to Fourier must be represented by this example, this form. So we need to find Fourier coefficients. So first of all, let me find out the DC component. So this is the expression to find out the DC component. So as I mentioned, we need to take this integration over a time interval which should be equal to t. Okay, this signal is, as you can see, it is symmetric with respect to this time. Okay, so I can take this interval. I can start from minus t by 2 and I can go up to plus t by 2. So I will say 1 over t and from minus t by 2 to plus t. Of course, you can take any interval you like. You can also take 0 to t. It's up to you. Okay, you can take 0 to t. You can take t to capital 2t, as long as interval is t. That's fine enough. But whenever you are dealing with a symmetric signal, it's better to take the interval such that you take half negative interval and half positive interval. And that is what I have done. I started from minus t by 2 and up to plus t. And then I need to integrate x of t. So of course, from minus t by 2 to minus t1 signal is 0. The signal is non-zero only between minus t1 to plus t1, and it is equal to 1. So this integral will only include minus t1 to plus t1. So it means it will be minus t1 to plus t1. And within this interval, what is the value? It's equal to 1. So it means you get constant signal equal to 2t1 by k. This is the constant or DC component that is present in this periodic square. Okay. Now, what are the other components? That is when k is not equal to 0. This was for k equal to 0. So for k not equal to 0, then we have to use this expression. Again, over we have to integrate over interval equal to 1 period. And again, for my convenience, I will take this interval minus t. As a result, we only need to integrate between this interval where the signal is non-zero and it is equal to 1. We will be left only with this thing. Now, this is a simple integral that you can easily solve. So I'm going to write down the answer that you will get ak equal to 2 sine k omega naught t1 divided by k omega naught. So this is what you get for this periodic signal. This is for k not equal to 0, and this is for k equal to 0. We can also simplify this expression because we know that omega naught is equal to 2 pi by capital T, which means omega naught t is equal to 2 pi. So it means this omega naught t, we can replace it with 2 pi. So what will happen? This 2 will cancel out, and this expression will be simplified to simply sine k omega naught t1 divided by k pi for k not equal to 0. Now, if you plot this, if you plot these Fourier coefficients, so this is a0 and then for different values, so you can find a1, a minus 1, a2, a minus 2. You will find out that if you put different values, so let me go back to the figure. This is actually the plot of the signal, but let me first write down the Fourier coefficients. So what you will get, okay, before I will talk about this, let me see what is the difference. These three graphs are given for different cases. The first case, this one. This case is for when time period t is equal to 4 times t1. Okay. This B is plotted for the case when t is equal to 8 times t1. And this figure C is plotted for the case when capital T is equal to 16 times T1. And what is T1? T1 is this interval where signal is non-zero. So we are keeping T1 is fixed. Okay. So this T1 is fixed. So what is actually changing? T is changing. As you can see, T is increasing. It means we have increased the time period. Okay. So I will say T is increased. And then we have plotted Fourier coefficients. So what is plotted over here? Because in this case, Fourier series coefficients are real. So these are, you can see this is a real number. So you only need one graph. You don't need two graphs. Okay. This is only plot of the magnitude. This is the plot of the magnitude. So what is actually changing? When you increase a period, so what happens to the frequency? So omega naught is decreased. Omega naught is decreased. So it means the different Fourier coefficients that you will get. So let's say a naught A1 and A minus 1, A2, A minus 2, A3, A minus 3. So these are different coefficients that are plotted over here. But I just want to show you the effect of this t increasing. Because frequency is decreasing, it means the Fourier coefficients will come closer to one another. So what will happen? AK will get closer to one another. And the point is, if you remember, this is k is a discrete number, so it is 0. So of course, this is same for all cases. Okay, DC component is the same for all. In this case, this 1 correspond to omega naught. In this case as well, this 1 correspond to omega naught. But now, because omega naught is decreasing, so this 1, even though it's correspond to omega naught, but this is now closer. It is getting closer to this DC component. Okay, so the difference that you can see in the plot of the Fourier coefficient is because of the reason that the period of the signal is changing. You are dealing with a square wave, but what is actually happening? Let me show you this graph. Let's assume that this is one square. Okay, what is going to happen if you change the period? It means now this is another same square wave, but you have increased its period. This is periodic. This is periodic. So what is going to happen to the Fourier coefficients? And Fourier coefficient, if you remember, it is telling you about the spectrum of this. So because period has changed, so Fourier coefficient behavior will change. And I have just given you a general trend that when t is increasing, as it is increasing, it is 4 times t1, 8 times t1, 16 times t1. So period is increasing. So what is going to happen? Omega naught is going to decrease. And the effect of omega naught is, what is the effect of omega naught? It means Fourier coefficients will get closer to one another. That is the effect that you can see in this particular figure. Okay. Now coming to the important question, and that question was raised by famous scientists of during the era of Fourier. They objected to this example that I just show you, square wave. So square wave is a signal or a function which is discontinuous. So if you look at square wave, you can see that there is discontinuity in this signal. You can see what is the behavior at these points. We have discontinuity. So this is a periodic signal. But what is the main point that I'm emphasizing? That this is a discontinuous periodic signal. So for Fourier, it doesn't matter whether signal is discontinuous or continuous. If it is periodic, according to Fourier, it will have a Fourier series. So any periodic signal could be represented by a Fourier series. This was the claim of Fourier. Joseph Fourier. So Joseph Fourier was a French physicist, and this was his claim that any periodic signal could be represented by Fourier series. But what was the objection of other renowned scientists of that era? They objected to this idea that how can this discontinuous signal be represented by a linear combination of continuous signals. So if you look at the Fourier series representation, this set of signal is continuous. Okay, for different values of k, if you put different values, whatever the signal you get, that signal is continuous. So they were not ready to accept this idea that by adding, of course, when you say linear combinations, actually you are adding a number of continuous signal. So the scientists who were not ready to accept the idea of Fourier, that how can a signal like this, which is discontinuous, be represented by addition of continuous signal? That was the major objection to the idea of Fourier. Now, what we know today is that Fourier was not correct in the sense that all periodic signal would have a Fourier series. We will talk about the condition under which periodic signal will have a Fourier series. So now we know that Fourier claim was not true. Any periodic signal can be represented, it is not. As well as the other scientists were also wrong. Their idea that discontinuous periodic signal cannot have Fourier series. Now we know that even if signal is discontinuous, it could have a Fourier series. So now, how can we answer this question? That which type of periodic signal will have Fourier series representation? So let me put this question. So what type of periodic signals could be represented by Fourier series? To answer this question, let's do some analysis. So the Fourier series that we have derived so far, it includes a linear combination of infinite number of terms. You can see that we are going to sum from minus infinity to plus infinity. So there are infinite number of signals, and we are adding them together, and as a result, we will be able to get exactly x of t. Let's replace this infinite Fourier series by finite Fourier series. In other words, rather than taking finite terms, let's assume that we only consider the terms from minus n to plus. So I call this as truncated Fourier series. And I'm going to represent this by x sub n. We indicate that this is a truncated Fourier series. Truncated Fourier series. And because we are not taking all of the terms, so it means the actual signal, which is x of t, and the signal that we will get by taking the finite number of terms, there will be difference in that. So we can call that difference as error. So I'm calling this signal as E and T. So what is this representing? This is representing approximation error. So it means original signal, which is x of t, and when I use the truncated Fourier series, which is taking the finite number of terms in the summation, there will be some difference, and that difference is represented by this. Now, in order to find out how good this approximation is, we need to quantify the size of this error. So how much is the size of the error? To determine the size of the error, we can find out how much is the energy present in this signal. So I will say to quantify the approximation error, we will use the energy in the error over one period. What we need to do? We need to take the error signal, which is represented by this, and then we need to take its magnitude and then square it, and then integrate it over one period. And whatever result we will get, we will call it as En. And En is the energy present in the error signal. Now, if you want to improve your approximation, of course, you will want En to be as small as possible. So I'm not going into the detailed derivation of this concept, but it has been mathematically proved by many scientists that if I want to use a truncated Fourier series, and if I want to make sure that energy in the error is as small as possible, so that my approximation is as accurate as possible, the Fourier coefficients must be equal to 1 over t integration over one interval, one period, e power minus j k omega naught t. So I will say to make minimum, use ak equal to this. So this is something which many scientists have proved this. But what is the important result that we can identify? To reduce the energy for the truncated Fourier series, the expression of ak is exactly similar to the expression that we use for when we use infinite Fourier series. If you remember, in this expression, how we calculate ak? We calculate ak with the help of this expression. And this expression is exactly similar to this expression. So what is the point? The point is, if you want to use a finite Fourier series and you want to get the best approximation, you can still use the same expression of Fourier coefficient that you use for infinite Fourier series. And another important point, of course, this error, we can minimize it, but it will not be zero if we use finite or truncated Fourier series. If I want to make En equal to 0, what should I do? I need to make this n approach to infinity. So I will say as n approaches to infinity, the error present in the approximation will approach to 0. As a result, this signal and this signal will be exactly similar. But that can only happen if we use infinite number. But still, what is the answer to this question? What type of periodic signals could be represented by Fourier series? That is the question that we still need to answer. So there are two set of conditions which people have proposed. So whenever these conditions are satisfied by any periodic signal, it will have a Fourier series. Okay. So let me write those conditions, and then we will talk about which type of signals cannot satisfy these conditions. So conditions. So as I mentioned, there are two possible set of. First condition is signals having finite energy over a single period. That is, mathematically, it means if you have a periodic signal, if you take its energy, that is, take its magnitude, square it, and then integrate it over one period. And if this answer is less than infinity, it means this signal has finite energy over a single period, over a single period. If any periodic signal fulfills this condition, then it will have a Fourier series representation. So one important point that you also need to understand is when we say that x of t is having a Fourier series like this, it means we should be able to find all Fourier coefficients. And it's also important that all Fourier coefficients are finite, because if you get any Fourier coefficients infinite, and when you take the sum, so it's not possible to take the summation of infinite number. So whenever you get ak infinite, it means for that periodic signal, there is no Fourier series. So first, mathematically, it's also important that we will say that mathematically, if signal has Fourier series, then all Fourier coefficients must be finite. That is mathematical interpretation. Another interpretation is even it's also possible that you get Fourier coefficients finite, but when you take the sum, and you can see summation is over infinite range from minus infinity to plus infinity. So even it is also possible that Fourier coefficients are finite, but when you take the summation, your result may diverge, or it may approach to infinity. Even then, your signal will not have Fourier. So what is the effect of this condition? When your signal has finite energy, what is the effect of this on the Fourier series signal? So let me write this. When this condition is satisfied, we are guaranteed. So we have a guarantee that the coefficients ak are finite. So first, mathematical difficulty will be overcome if you are having a signal which is having a finite energy. Okay. And what is the other effect of this condition? And if for such signals which is fulfilling this condition, if we use a finite Fourier series, which means if you take summation from minus n to plus n, and you get a signal xn2. And then what will be the error? Error in the approximation will be x of t minus this thing. And for finite Fourier series, this one, we are guaranteed that energy En in the approximation, that is E of t, converges to zero as n approaches to infinity. So that is the other effect of what's there. So let me write this in red color. What is the meaning of this? It means that if you take the energy of a signal and if you take it over one period, the answer will come out to be. And that is very important result. It is telling that when you have a signal, periodic signal, which is having finite energy over a single period, we are saying that this type of signal will have a Fourier series representation. And then we are looking at this question that what will happen to the Fourier series if we use finite number of terms. So of course, when you use finite number of terms, there will be difference between the actual signal and the approximated signal, which we are representing as this signal. But if you calculate the energy of this signal, energy present in this error signal will be zero. So in terms of energy, there is going to be no difference between the original signal and the truncated signal. And this concept is important from communication system point of view, that even though there can be difference in the two signals, but if their energy is same, so all system will treat those signals identically. So the difference in two signals is decided based on the energy of the signal. So even x of t and this signal may be different, but if they have this condition, it means there is no difference in the energy present in this signal and this signal. So it means our actual signal and its Fourier series representation will be identical. So that is the effect of this condition. Okay? Then we are going to talk about another set of condition which is known as Dirichlet conditions. So these conditions are more comprehensive. Okay, so there are three conditions proposed by Dirichlet, and if these three conditions are satisfied by any periodic signal, it will have a Fourier series representation. So let me write down those conditions one by one. Condition number one: over any period, x of t must be absolutely integrable. Which means, what is the mathematical form of this condition? If you take a signal, if you take its magnitude, and if you take its integral over any one period, this should be finite. This is condition number one. Let me write down condition number two. In any finite interval, x of t is of bounded variation. That is, what is the meaning of this thing? Bounded variation means that is, there are no more than a finite number of maxima and minimas during any single period of the signal. And I will come back to the explanation of these three conditions. Let me write the third and final condition, which is part of a broad category of Dirichlet condition. What is the third condition that periodic signal must satisfy? In any finite interval, there are only a finite number of discontinuities. Furthermore, each of these discontinuities is finite. So these are three conditions which were proposed by Dirichlet. And any periodic signal, if it has Fourier series representation, it must satisfy all of these three conditions. Now, it may seem that which signal will not satisfy this first condition. So there is a signal which is periodic, but it is not absolutely integrable. Okay. So let me give you the graphical example for such type of signal. This is signal which doesn't satisfy condition number one. You can see the signal is periodic. It is repeating itself after this time interval, but it is not absolutely integrable. If you integrate this from 0 to 1, you can see area under this graph is infinite. So it doesn't satisfy condition number 2. Okay. Similarly, this, if you look at this example, we mentioned that over any finite and time interval, there should be finite number of maximas and minimas. So this is the signal which is periodic, but it doesn't satisfy condition number 2. So from this time interval to this, you can see there are it has many maximas and minimas very within the finite time interval over here. So it doesn't satisfy condition number 2. And this third signal is an example which doesn't satisfy third condition of Dirichlet. And what is that third condition? There should be finite number of discontinuities within finite time interval, as well as the value of the discontinuity should be finite. You can see within this finite interval, 0 to 8 is the period of the signal. You can see there are many discontinuities. There are many discontinuities. So this particular signal doesn't satisfy condition. Now, it may appear that Fourier was, as I mentioned initially, that Fourier was not correct by claiming that any periodic signal will have a Fourier series. And now this is slide is telling you an example of periodic signals. So according to Fourier, these signals must have Fourier series. But now we know these three signals doesn't have Fourier series. But the important point is these signals, they doesn't come into picture in real systems. So these are just mathematical signals. most of the signal that you will deal in practical systems, they will fulfill condition number 1, condition number 2, as well as condition number 3. So it will be very rare that you will be encountering a signal which will be something like this, something like this, or something like this. So what we can now claim is that all practical periodic signals, all realizable periodic signals, all of them have Fourier series representation. Okay, so that's enough for today's lecture. Thank you very much. See you next time.